Hi dear students, this is the 8th part of 4th module ME 206 fluid machinery. In the last part we have seen the working of the air vessel and the applications of the air vessel. In this presentation we will see the work saved by fitting air vessel. We are dividing this into two parts. First we will see the work saved by fitting air vessel in the case of single acting pump, and then we will derive work saved by fitting air vessel in the double acting pipe. Now let capital A equal to cross sectional area of the cylinder and small a cross sectional area of the suction bar delivery pipe, LD length of the delivery pipe above the air vessel, and LD dash length of the delivery pipe between the cylinder and air vessel. I can show the figure. Here it is. See, LD dash is the length of the length from the center of the cylinder to the air to the point where the air vessel is fitted. That is, this small distance is LD dash, and the remaining length of the delivery pipe is LD. Similarly, the distance from the center of the pipe to where the air vessel is fitted in the suction side, this length is taken as LS dash, and the remaining suction pipe length is taken as LS. So usually LS dash and LD dash length compared to LS value and LD value will be very small, so we will be neglecting all this length. So that we have seen in the last part itself. Now coming to the derivation, LS is length of the suction pipe below air vessel, LS dash length of the suction pipe between air vessel and the cylinder, HAD acceleration pressure in the delivery pipe, HAS acceleration pressure in the suction pipe. We are having the equation to calculate these two heads, but we know that if you are considering the work, if you are calculating the work done or work required, then in that case this term is not coming, because even though HAD, HS, whatever may be the value of HAS and HAD, it won't make any sense in calculating the work required, because the area of the indicator diagram remains constant whatever may be the value of HAS and HAD. That also we have already seen now. But in the case of frictional effect, it is not like that. The area, if there is a HF value and HFD value, the area is getting increased. So HFD head loss due to friction in the delivery pipe, and HFS head loss due to friction in the suction pipe. Now first case is work done against friction without air vessel. We are considering the air vessel is not fitted with, we are considering the reciprocating pump not fitted with the air vessel. In that case what happens is the flow in the entire suction pipe and delivery pipe will be depending on the crank angle theta, so it won't be uniform. Based on the theta value, the velocity will be varying inside suction pipe and delivery pipe. Once the air vessel is fitted, what happens is the flow becomes uniform through the entire length of the suction pipe as well as the delivery pipe. That is the advantage of fitting air vessel. Now if the pipe is not fitted with air vessel, the velocity in suction bar delivery pipe will depend on the crank angle theta, and velocity of flow is given by V is equal to A by A omega r sin theta. This we have derived in the first part. Please refer back. So anyway, we are having the direct equation V is equal to A by A omega r sin theta. See, it is depending on the value of the sin theta. Head loss due to friction HF is equal to 4FL V square by 2GD. So 4FL by 2GD into, instead of velocity we will be substituting A by A omega r sin theta. So A by A omega r sin theta whole square. At the beginning and end of the stroke, theta will be, whether it is suction or delivery, whatever may be, theta value is 0 at beginning and 180 at the end. So at the beginning and end, this term sin theta term is going to be 0, so entire term becomes 0. So at the starting and ending end portion, HF value will be HF, whether it is HFS or HFD, it is 0. At the middle, theta equal 90 degree, we will have maximum HF value, that is given by 4FL by 2GD A by A omega r whole square. Sin theta becomes 1. So that is the HF max. Now we know that work done per stroke against friction is directly proportional to area of the indicator diagram. So due to the frictional effect, the indicator, what happens to the indicator diagram is one parabolic area is added to the indicator diagram. So HF max having this length as stroke length and this height as HF max. If you are talking about the delivery side, then it is HFD max. Among the suction side, we will have this length as HFS max. So in general, the area of the indicator diagram added along with the ideal indicator diagram is area of the parabola, that is equal to 2 by 3. Usually the area of the parabola is given by 2 by 3 into stroke, this 2 by 3 into base into height, that is the area of the indicator parabola. So here base is stroke length L and height is HF max. So work done per second is work done per stroke, not work done per second. Actually, work done per stroke is directly proportional to 2 by 3 into L into HF max. This term is the area of the indicator diagram due to friction. So work done per stroke is directly proportional to 2 by 3 into L into instead of HF max, I will substitute 4FL by 2 GD A by A omega r whole square. So since it is work done per stroke, now work done per second is I am taking it as W1 is obtained by multiplying the area of the indicator diagram with a constant of proportionality, that is K. That K I have already explained is rho g an by 60 in the case of single acting. In the case of double acting it will be 2 rho g an by 60. So here it is single acting. So rho g an by 60 into area of the indicator diagram will be the work done per second, that is W1 equal to rho g an by 60 into 2 by 3 into L into 4FL by 2 GD into A by A omega r whole square. This I have substituted here, that's all. Now W1 equal to rho g ALN by 60, I have taken this L along with this term, that's all. Rho g ALN by 60 into the remaining is 4FL by here this 3 is taken along with this one, so 3 GD into A by A omega r whole square. Okay, this 2 and this 2 will get cancelled. So the remaining is 4FL by 3 GD A by A omega r whole square. Now next case is work done against friction with the air vessel. As I have already told, if the air vessel is there, the flow velocity in the suction pipe and delivery pipe will be uniform. It won't depend on the value of the theta. So if you want to calculate the uniform velocity, how we will get is, we know that discharge equal to area into velocity. So before that, what happens is, if the flow velocity becomes uniform, the shape of the indicator diagram becomes a rectangle. Since from starting to ending, HF value will be HF max value. This value is going to be constant since flow velocity is constant. So it is a rectangular shape. But remember, this is not the HF as calculated in the earlier case. There HF is calculated with varying velocity. Here it is going to be calculated with uniform velocity. That is the difference. Anyway, this shape is going to be a rectangle. Remember about this. Where x-axis we have the stroke length and y-axis we have HF. Now if you want to calculate the average velocity of flow in the suction pipe or delivery pipe, we have the general equation Q is equal to area into velocity. So total Q in Q means Q per stroke is nothing but Q inside the cylinder. Q is in the case of single acting pump, we have Q equal to ln by 60. That is the equation to calculate Q. So that Q equal to area of cross section of the pipe into velocity of flow in the pipe. So we will equate from that equation we will get small v, that is average velocity of flow or uniform velocity of flow in the suction or delivery pipe is ln by 60, that is Q by small a, where a is the cross sectional area of suction pipe or delivery pipe, whatever it may be. So this is the equation to calculate V. Earlier we have some other equation, that is here we have used equation to calculate V as V is equal to A by A omega r sin theta, since here the velocity was not uniform, but here we are using that uniform velocity. V is equal to ln by 60 by A. Okay, now we have omega equal to 2 pi n by 60, angular velocity omega equal to 2 pi n by 60, and n by 60 equal to omega by 2 pi. So n by 60 equal to 2 pi is taken other side, therefore n by 60 equal to omega by 2 pi, and we have L is equal to 2r. Now substituting these two in this equation, instead of n by 60 we are substituting omega by 2 pi, and instead of L we are substituting 2r. Therefore average velocity becomes V is equal to A by A omega r by pi. In the earlier case only difference was their velocity was A by A omega r. Here divided by pi is also coming, that's the only difference. Now using this velocity we will be calculating the value of HF, head loss due to friction HF equal to 4FL by 2 GD V square, that is the equation. Here instead of V we will be substituting this value, so 4FL by 2 GD into A by A omega r by pi whole square. Now area under the indicator diagram, as I told, it will be a rectangle, so L into HF will be the area of the indicator diagram. So L into HF is 4FL by 2 GD A by A omega r by pi whole square. Now work done per second is area of the indicator diagram multiplied by rho g n by 60, since it is a single acting pump. So W2, I am taking that value of W2 work done per second. W2 equal to rho g n by 60 into L into 4FL by 2 GD A by A omega r by pi whole square. So I am taking this L along with this one, so it becomes W2 equal to rho g ALN by 60 into 4FL by 2 GD A by A omega r by pi whole square. Now if you want to calculate the work savings in percentage, usually what we will do is higher value minus lower value divided by higher value into 100, that will be the saving in work. So here W1 that is work done, work without air vessel will be greater, and with the air vessel we have to we require less work only. So W1 minus W2 by W1 into 100 will be the saving in work done. So W1 by W1 is 1. So 1 minus W2 by W1 into 100. So 1 minus W2 means work done with the air vessel, and W1 is work done without air vessel. Now substituting for W2 here, that is rho g ln by 60 into 4FL by 2GD A by A omega R by pi whole square, and here I am substituting for W1, that is equal to rho g ln by 60 into 4 by 3 4FL by GD into A by A omega R whole square into 100. So this term, this and this will get cancelled. Simplifying the most of the other terms here are constant. Simplifying all other terms, the remaining term will be 1 minus this entire term becomes 3 by 2 into pi square into 100. So substituting for pi equal to 3.14, you will get it as 84.8%. So by fitting an air vessel in the single acting pump, this much work can be saved. That is the importance of the fitting air vessel in the single acting pump. Now we will see the work saved by fitting air vessel in the double acting pump. Work saved by fitting air vessel in the double acting pump. Case 1, work done against friction without. We will be going in the same fashion as in the earlier case. This side we don't have much changes. Case 1, work done against friction without air vessel. First we will consider without air vessel. If the air vessel is not fitted, the flow velocity in the suction bar delivery pipe will depend on the crank angle theta. So velocity of flow is given by V equal to A by A omega R sin theta, or in the earlier I have explained earlier. So I am going little bit fast. So head loss due to friction HF equal to 4FL by 2GD V square. So 4FL by 2GD, instead of V we will be substituting this one. As we know, at the starting and end theta value will be 0, sin theta value will be 0. So we will have the maximum value at the middle of the stroke, theta equal to 90 degrees. So HF max equal to 4FL by 2GD A by A omega R whole square. Same as in the earlier case. Now work done, this also is same. Now work done per stroke against friction is directly proportional to area of the indicator diagram. Work done per stroke is directly proportional to area of the indicator diagram is area of the parabola, that is 2 by 3 into L into HF max. Now work done per second is directly proportional to 2 by 3 into L into 4FL by 2GD into A by A omega R whole square. I am taking this value as work done per second value as W1, that is equal to rho g n by 60 into area of the indicator diagram. That is W1 equal to here, since it is double acting pump, here we have to multiply 2 rho g n by 60. Sorry, this is a mistake. Here we have to multiply 2 rho g n by 60 into area of the indicator, that is W1 equal to 2 into rho g n by 60 into 2 by 3 into L into 4FL by 2GD A by A omega R whole square. Therefore W1 equal to 2 rho g ln by 60 into 4FL by 3GD A by A omega R whole square. We have seen it in the earlier case also. Only difference is here 1 2 is coming, that's all other terms remains constant, same as in the earlier case. So now here we have the change, that is work done against friction with air vessel. We are considering the reciprocating pump with air vessel. By fitting air vessel, the flow velocity of course will be uniform. So we have to find out the average velocity to find out the HF value. So average velocity of flow equal to discharge by cross sectional area of the pipe. So average velocity V equal to discharges of the double acting pump is 2 A ln by 60. So divided by area of the pipe, A will give the average velocity. V is equal to 2 ln by 60 by A, but omega equal to 2 pi n by 60 and n by 60 equal to omega by 2 pi and L is equal to 2R. So rearranging as in the earlier case, we will get V equal to 2A by A into omega R by 2 pi. Here 2 is coming extra, that's all. So head loss due to friction HF equal to 4FL by 2GD into V square. So 4FL by 2GD into 2A by A omega R by 2 pi whole square. Now area of the indicator diagram is equal to L into HF. Since the area of the shape of the indicator diagram becomes a shape that of a rectangle, so area will be L into HF. So that's equal to L into 4FL by 2GD into 2A by A omega R by pi whole square. Now work done per second against friction equal to 2 rho g n by 60 into area of the indicator diagram. So W2 equal to 2 rho g n by 60 into L into 4FL by 2GD into 2A by A omega R by pi whole square. I am taking this L along with this term. So rho g ln by 60 into 4FL by 2GD into 2A by A omega R by 2 pi whole square. Now savings is W1 minus W2 by W1 into 100, that is equal to 1 minus W2 by W1 into 100. So substituting for W2 here and W1 here, you write it in a paper and simplify it. you will get this terms and all will be directly vanishing. 2 rho g ln by 60 is here, here also 2 rho g ln by 60 will get cancelled. FL by GD, FL by GD, everything is here. 4 and 4 will get cancelled. Here it is 3 by 2. If 3 is going up, it will become 3 by 2. But here 2 is there, that will be coming outside. So finally it will become 1 minus 6 by 2 pi square. That will be the final term. You simplify this one in a paper, write it in a paper and simplify. You will get 1 minus 6 by 2 into pi square into 100. So if you substitute for pi equal 3.14, you will get 39.21% of work is saved by fitting air vessel in the case of double acting pump. So in the case of single acting pump, it was very high. We can save a lot of work, but in the case of double acting pump, by fitting air vessel, this much amount of work can be saved, that is 39.21. So this much less amount of work is to be provided. That is the importance of fitting air vessels. So it indirectly it is proof that by fitting air vessel we can reduce the work requirement of a reciprocating. Otherwise we are losing a lot of energy, a lot of work to overcome the frictional effect. That's all. Now we will see a problem from this side. That is, a double acting reciprocating pump is fitted with an air vessel on the suction side close to the pump. So to the suction side air vessel is fitted. The suction lift of the pump is 4.